So in today's lecture, we're going to be talking about forces and Newton's equations. So in the past couple of lectures, we've talked about things moving in 1 and 2 dimensions. We've talked about positions, we've talked about velocities and accelerations, and how they all intertwine with one another. We know that velocities change positions, and we know that accelerations change velocities. But we're missing something from our prescription of physical motion, right? Where do those accelerations come from? We know that when we push or pull on a chair, something about that action causes the chair to move, provided that we've applied enough muscle and that we've applied it in the proper direction. So it's in this lecture that we're going to make the connection between those pushing and pulling actions, which we call forces, and the results that they have on the objects that they're acting on. So to begin with, we're going to be talking about Newton's 3 laws. So in his first law, Newton states, so for his first law, so in Newton's first law, he states that an object continues in a state of rest. An object continues in a state of rest or in a state of motion, or in a state of motion at a constant velocity. Constant velocity, unless compelled to change that state by a net force. Unless compelled to change that state by something called a net force. Now I want to point out that if an object is at rest, right, that is an example of a constant velocity, right? It's just that the velocity is 0. So it doesn't seem like much, but Newton's first law tells us that there are things called forces. And at this point, all the first law really tells us is that forces are what forces do. They act on objects to change their velocities. Conversely, the first law says that if the net force acting on an object is 0, then the velocity of the object won't change. So no net force, no change in velocity. So here I'd like to introduce a definition of sorts. And it's going to be the definition of inertia and mass. Let me zoom out a little bit. So definition. Inertia and mass. So this is going to be like a sort of a pseudo definition. So this says that inertia is the natural tendency of an object. Is the natural tendency of an object to remain at rest or in motion. To remain at rest or in motion at a constant velocity. At a constant velocity. Right? Objects are lazy. If they're moving or if they're at rest, they don't want to change. So the mass of an object, is a quantitative measure of inertia. Is a quantitative measure, right? We can measure it. It's a quantitative measure of inertia. Right, so if there's a baseball coming at you, at 10 meters per second, ostensibly you can put up your hand and catch it, and changing its motion isn't too bad. However, if there's a train coming at you at 10 meters per second and you try and stop it, that won't work out very well for you. And that's because the train has a lot more mass, therefore it has a lot more inertia. And it's going to be harder to change its motion as compared to the much lighter baseball. So the units of mass, and I've talked about this before, but the units of mass that we're going to want to be working in are going to be in units of kilograms. All right, so that's what we're going to want to stick with. Now, in his second law, Newton states that the sum of the forces acting on an object are equal to the mass times the net acceleration of an object. So here, I'm going to write down Newton's second law. So the second law states that the sum of the forces acting on an object is equal to the mass times the net acceleration of that object. So here on the left-hand side, these are just forces. You can think of them as vectors, just like individual vectors, nothing more, nothing less. And this symbol here just means we're adding all of them up. All right, so if you have three forces, then you're going to have F1 plus F2 plus F3, and that's going to be your net force. And then on the right-hand side, we have our mass, and then here is our acceleration. So this term here is what we call the net force. This term right here is the mass of our object. And then this term right here is our acceleration. Right. So again, in his second law, Newton states that the sum of the forces acting on an object, the sum of the forces, are equal to the mass times the net acceleration of the object. So here we see the first tangible result relating the forces that Newton talked about. Right, so we talks about the forces. It relates those forces that Newton talked about to the acceleration of an object. So his second law tells us that forces are vector quantities with both a magnitude and a direction, and that when you add up all the forces on an object, right, when you add up all the forces, you get the net force acting on the object, and that is going to be equal to the mass times the net acceleration of the object. So keeping in mind that adding two vectors together gives you another vector, the left side of Newton's second law then says that the sum of forces acting on an object will result in another vector, which we call the net force acting on the object. This net force will have a magnitude and direction by virtue of being a vector. And while keeping this in mind, then Newton's second law states that the acceleration of an object is equal to this net force divided by the mass of the object. That is, the acceleration vector for an object will point in the same direction as the net force vector. That's an important point. So in words or in equations, this is saying that the acceleration that an object feels, actually, let me move it down here a little bit. The acceleration that an object feels is equal to the sum of the forces acting on that object divided by the mass. So this is an important point, so I'm going to box it off. All right. So our acceleration that our object experiences is going to be equal to the sum of the forces divided by our mass. So for the same net force, right, if the sum of our forces is the same, but we have a heavier object, then our acceleration will be smaller, right? So for example, if you're trying to, I don't know, push your nephew on a bike, right? If you apply 10 newtons of force, then you can accelerate your cousin to whatever. But if you try and apply 10 newtons of force to a car that's parked in neutral, right, it's going to accelerate a lot more slowly just because it's heavier, right? This mass value is larger. And so the unit of force, might as well introduce it at this point. Already mentioned it, but it's good just to be explicit. So the unit of force is going to be equal to the kilogram times meter per second squared, right? It's going to be the units of mass in kilograms and the units of acceleration, which is meters per second squared. But physicists are lazy, and we don't always want to write kilograms times meters per second squared. So we've defined another unit, capital N, where N is called the Newton. If you invent physics, I think you deserve to have a unit named after you. So here I've got GeoGebra opened up again, and I want to show you guys an example where we have a bunch of forces acting on an object. This object is located here at the center, the origin, 0, 0. And we want to find the net force acting on this object. So we have 3 forces, F1, F2, and F3, and they're all acting in different directions on the object. So if we add all of these together, right, then our net force can be equal to this point here. So I don't know how to make GeoGebra actually point from here to here. But the net force in this case, when you add all these vectors together, it's going to give you another vector. It's called the net force, and it's going to point from the origin where our object is, and it's going to point to this point right here with an x coordinate of 1 and a y coordinate of 3. So forces aren't anything new or scary or anything like that. If you guys are already comfortable with vectors, as you should be, then this stuff is not going to be any more difficult than anything that you've seen in the past. So with all that being said, let's work out a quick example. Just going to zoom out a little bit. So for our first example, close example 1. So in the first example, a person is pulling a box. Person is pulling a box of weight or of mass 20 kilograms. Of mass 20 kilograms with a rope. With a rope. Problem says that the acceleration of the box, the acceleration of the box is 5 meters per second squared. So the problem wants us to find the magnitude of the force exerted by the person. Find the magnitude of the force exerted by the person. All right. So to begin with, the mass of the box we know is 20 kilograms. And we know that it accelerates with an acceleration of 5 meters per second squared. So since this is a 1D problem, the box is accelerating to the right with an acceleration of 5 meters per second squared. So the problem doesn't list any other types of forces acting on the box aside from the person pulling on it with a rope. So in that case, the magnitude of the force exerted by the person on the box is going to be equal to the mass of the box times the magnitude of the acceleration. So this is going to be 20 kilograms multiplied by 5 meters per second squared, which is going to be 100 kilograms times meters per second squared for the units. And keep in mind that a kilogram times a meters per second squared is going to be equal to 1 Newton. So we say that the magnitude of the force that the man exerts in the box is 100 newtons of force. So that's our first example. So let's look at one more example. So this is going to be example 2. So for example 2, it says that a person is pulling a box. A person is pulling a box with a force F1 that has a magnitude of 5 newtons. And another person is pushing the box. And another person is pushing the box. Pushing the box with a force F2 that has a magnitude of 10 newtons. 10 newtons. Problem goes on to say that there is friction between the box. There is friction between the box and the surface. Between the box and the surface that it's sliding on. So just the surface. With friction force with a friction force of, I'm gonna do a little f, and that magnitude is 7 newtons. 7 newtons. Right. So the problem wants us to find the acceleration of the box if it weighs 10 kilograms. Find the acceleration of the box if it has a mass 10 kilograms. Part B is asking us if the box starts from rest. If the box starts from rest, find the box's displacement after 1 minute. Find the box's displacement after 1 minute. And last but not least, part C wants us to find the velocity of the box. Velocity of the box after 5 minutes. 5 minutes. Zoom out a little. So in these cases, it always helps to draw a picture. So in this case, we have the ground. We have our box. Looks like that. Right. So we have one person pushing on the box. So I guess I'll draw that in red. So we have one person pushing on the box. Some force F1. We have another person pushing on the box. F2. Now, last but not least, we have the friction force, which is going to oppose the direction of our box. So this force F, our friction force. So this is the first time that we've seen friction in this course. And something that I just want to say right off the bat is that friction always opposes the intended direction of an object's motion. So just a little side note here, friction. Right, whenever something is making contact with another surface and they're moving relative to one another, so in case this box is sliding over the ground, so friction always is pointing in the direction opposite the object's intended motion is pointing in. Right. So in this case, our box is being moved to the right by these people that are pushing and pulling on the box. And so the friction force is going to be opposing that motion. And so let's try and solve this. Okay. So in this case, we have two forces that are pointing to the right. We have the force F1 and F2 pointing to the right. And then we have the friction force pointing to the left. So first, we're going to add up all of our forces. Add up all of our forces together. That's going to be equal to the mass of the box times our acceleration. So the way that we usually deal with force problems is we first draw a picture, which we've already done. And the second thing that we like to do is we need to take all these forces, which are vectors, and we need to break them up into their x and y components. Now, in this case, it's particularly easy because, the forces F1 and F2 were just pointing to the right, and our frictional force is pointing to the left. So in this case, this is kind of an example of a one-dimensional problem because the box is either going to go to the right or to the left. In this case, the box is going to go to the right. So the sum of the forces on our object is equal to the mass times the net acceleration of our object. So let's write down our forces to begin with. So our first force is going to be entirely in the positive x direction. And this first force has a magnitude of 5 newtons. So 5 newtons. Now in this case, because this is a one-dimensional problem, the fact that this is a positive number indicates that it's pointing to the right, and negative indicates that it's pointing to the left, the usual. So F1 is equal to 5 newtons. Force F2, right, the person pushing on the box, is doing so with a magnitude of 10 newtons. So they're pushing on the box with force of 10 newtons to the right. And last but not least, our friction force, little f, is pointing to the left with a magnitude of 7 newtons. So it's going to be minus 7 newtons. Right? And so now when we add all of these forces together, right, these are all the forces acting on our box that we have listed. So we're going to add all these forces together to get that the sum of the forces, sum of the forces. It's going to be equal to F1 plus F2 plus F3, which is going to be 5 newtons, plus 10 newtons minus 7 newtons. If this were a two-dimensional force problem, this might be a little bit complicated because then we'd have to do, we'd have to look at the X component stuff and add that stuff up. Then we'd have to look at the Y component stuff and add that up. But it's really not too much more difficult than this, right? Usually the hardest part about force problems is drawing the picture and then breaking up the forces into their X and Y components. If you can do that, you've already surmounted the hardest part of these force problems. So on the left-hand side of this equation, we have the sum of our forces, which is equal to 5 plus 10, which is 15, minus 7 newtons. So the sum of our forces is 8 newtons. But the fact that this is positive indicates that the net force points to the right. So this is going to be equal to our mass, right, the mass of our box, times the net acceleration of our box. So the mass of our box is, what was it, 10 kilograms? Yeah, so part A says the acceleration of the box if it has a mass of 10 kilograms. So 10 kilograms times our acceleration. So now if I divide both sides by 10 kilograms, we get an acceleration of 0.8 meters per second squared. And again, the fact that this is positive indicates that this box is accelerating to the right, which you'll notice is in the same direction that our net force is in. Right? Now, part B is saying, if the box starts from rest, find the box's displacement after 1 minute. So we know that the position of our box in the X direction is equal to where our box starts plus how fast it's going in the X direction times time plus 1/2 times how fast it's accelerating in the X direction times time squared. So in our case, if we subtract off this X naught from both sides, we get X minus X naught, which is in fact the displacement of our box in the X direction. So this is what part B is asking for. So that's equal to the initial velocity in the X direction times time plus 1/2 times our acceleration in the X direction times time squared. But notice part B said if the box starts from rest. So if the box starts from rest, its initial velocity is 0, which means this whole thing is 0, because the initial velocity of this thing is 0. Right, so that's why that term is gone. And then the acceleration of the box in the X direction is simply what we found before. Right, the answer to part A is our acceleration in the X direction. So our displacement, delta X, is equal to 1/2 times our acceleration in the X direction, which is 0.8 meters per second squared, times time squared. Now our time is going to be 1 minute, but we know that 1 minute is equal to 60 seconds. So I'm just going to do a little bit of unit conversion on the fly there. And so when you multiply all this together, you get a displacement, delta X, a displacement of 1,440 meters. Like that. And last but not least, the problem wants us to look at the final velocity of the box after 5 minutes. So for part C, we know that the time is 5 minutes. And we know that there's 60 seconds in 1 minute. So the units of minutes cancel out. And then the unit of time that we have is now 5 times 60, or 300 seconds. Right. And we can find our final velocity relatively easily because we know that our final velocity in the x direction is equal to our initial velocity in the x direction plus our acceleration in the x direction times time. Now again, our box starts from rest, so this term is 0. And so our final velocity in the x direction is equal to our acceleration times time. But in this case, it's just going to be 0.8 meters per second squared times 300 seconds. So after 5 minutes, we get a velocity in the x direction, final velocity, of 240 meters per second. I don't know who these people are that are moving the box, but they're doing a very good job since this is much faster than most cars can move. And so with that, we've finished the second example. So like I've mentioned, since Newton's second law is a vector equation, right, both the left and right sides of the equation have vectors in them, we can break the second law up into its x and y versions of the second law. So we get one version of Newton's second law for each direction. So we're going to call that the vector decomposition of the second law. Vector decomposition of the second law. Just like that. So we start with Newton's second law, which is that when you add all the forces together that are acting on an object, it's going to be equal to the mass times the net acceleration of the object. But really, since this is a vector equation, these forces in general have, for working in 2D, they'll have an x component and a y component. So for the x component stuff, the x component version of Newton's second law, we have that the sum of the forces in the x direction, that's going to be equal to the mass times the net acceleration of our object in the x direction. Where on the left-hand side, this is just the x components for all of our vectors. And for our y component version of the Newton's second law, so y components right, if you've guessed that you just add up all the y components, and that's equal to the mass times the net acceleration in the y direction, then you'd be spot on. So now let's look at an example to sort of solidify this. So example, I think this is 3. I'm going to call it 3. I hope it's 3. So example 3 says that 2 forces are exerted on a box as following. So 2 forces are exerted on a box as following. And there's an associated picture, which I will draw after this. So the problem wants us to find, part A, the magnitude and direction of the net force, the magnitude and direction of the net force. And for part B, it's saying if the mass of the box is 2 kilograms, find the box's acceleration. Find box's acceleration. Okay, So let me draw the picture. So we have the ground. Actually, might draw a little lower. So we have the ground. We have our beautiful box. Expertly drawn by Da Vinci himself. So we have two forces acting on our box. Might be a good idea to draw axes like this. So this vertical axis is the y direction, horizontal axis is our x direction. So we have this force F1, which is pointing like this. So it's our force F1. Apparently has a magnitude of 15 newtons. And it's being applied at an angle of 30 degrees above the x-axis. And then we have a second force that's pulling it in the other direction. So this is a force F2, which has a magnitude of 5 newtons. Right. So it wants us to find the magnitude and direction of the net force. And it wants us to find the acceleration of the box if the mass of this box is 2 kilograms. So it's important to note in this problem, there's no friction. The problem has not explicitly said that there's friction, so we're not going to include friction. So we've drawn our picture. And this is an all right picture. But we can do one better. So it's a little ambiguous, like where these forces are acting, right? This one looks like it's pointing at the corner of the box. This one's actually pointing at one of the sides of the box. But really, they're all acting from the center of the box. The picture sort of doesn't do it justice. So what we're going to do is we're going to draw something that's called a free body diagram. So we're going to have our box like that. And the idea is, I might actually offset this a little bit. The idea is that we're going to draw our axes going through the center of our object. Right, where horizontal axis is our x-axis, our vertical axis is the y-axis, and our forces are going to be acting on the center of our box. So it's going to look like this. This is our force F1. Right, has a magnitude of 15 newtons. This angle here is 30 degrees. And then we have this other force, which points to the left like this. This is our force F2. And it has a magnitude of 5 newtons. Right. Okay, so this makes it a little clearer because now we can just decompose our two vectors, F1 and F2. We can decompose them into its x and y components. So to begin with, F1 is equal to some amount in the x direction, but we know how to find the x component of F1, right? So drop a right triangle like that. And solving this for its x component is just its magnitude, so 15 newtons, times cosine of the angle between it and the x-axis, which is 30 degrees. It's going to be its x component plus its y component, which is its magnitude times sine of its angle. Right, and that's going to be its y component. So that's F1. Now F2 is going to be equal to its magnitude, right? Its x component is going to be equal to its magnitude of 5 newtons times cosine of its angle between where it's pointing and the positive x-axis. So what is the angle between our positive x-axis and our vector f2? So in this case, f2 is pointing in the negative x direction. So starting from our positive x-axis, right, we have to go 90 degrees to get to the positive y-axis, plus an additional 90 degrees until we hit our vector f2. So in total, we've gone 90 degrees plus 90 degrees. So in total, we have 90 degrees plus 90 degrees is 180 degrees for our vector f2. So this is 180 in the x direction. And then for the y component of f2, we have its magnitude times sine 180 degrees, y direction. But notice if you look at f2, it's pointing entirely in the negative x direction. It's not pointing at all in the y or negative y direction. And which makes sense because when we break down the components of f2, we see that since sine of 180 degrees is equal to 0, we see that this whole term is 0. And furthermore, we know that cosine 180 degrees is equal to -1. So f2, our vector f2, is equal to -5 newtons in the x direction. So in our case, the y component of f2 is 0. Okay, so I'm going to break it down even further. So f1 is equal to, and here I'm just actually plugging in 15 times cosine of 30 and 15 times sine of 30 degrees, just so we have like some strict numbers to work with. So f1 is going to be equal to 13 newtons in the x direction plus 7.5 newtons the y direction. Then f2 is going to be -5 newtons in the x direction plus 0 newtons in the y direction. Okay, well, now that we have that all worked out, we can find the net force, F net. It's going to be equal to the sum of all the forces in our problem. All right, so this is just going to be F1 plus F2. So adding these two vectors together is the same as adding their x components together and adding their y components together. So in the x direction, we have F1's x component, which is 13 newtons, plus F2's x component, which is -5 newtons. That's our x component for our net force. And in the y direction, we have the y component for F1, 7.5 newtons, plus the y component for F2, which is 0. So, 7.5 plus 0 is just 7.5. So then we get that the net force is equal to 13 minus 5 newtons in the x direction, so 8 newtons in the x direction, plus 7.5 newtons, 7.5 newtons, plus 7.5 newtons in the y direction. And so now the magnitude of this net force is equal to the x component squared, so 8 newtons squared, plus the y component squared, so 7.5 newtons squared. We just take the square root of that. Right? So if you punch this into a calculator, you get that the net force magnitude is equal to about 10.97 newtons. 10.97 newtons. Right? And the direction we can figure out. So first of all, notice that the x component for our net force is positive, and the y component for our net force is positive. So it's in the first quadrant. So it's pointing a little bit to the right and a little bit up. And so we can figure out the direction the thing is pointing in, because theta for net force. It's going to be tangent inverse of the y component of our net force. So y component for our net force divided by the x component for our net force. This is tangent inverse of 7.5 divided by 8. Right, then we get a direction theta for our net force of about 43.15 degrees. Like 15 degrees. Right, but if you want to round it, it's just fine to call it 43 degrees. So part B is asking for the acceleration of the box if the box's mass is 2 kilograms. So for part B, the mass is 2 kilograms. And so the acceleration of this box is equal to our net force divided by the mass. So in this case, it's going to be our net force, which we found to be 8 newtons in the x direction, plus 7.5 newtons in the y direction, all divided by the mass of 2 kilograms. Right, so we get an acceleration vector of 8 divided by 2 in the x direction, so 4 meters per second squared in the x direction, plus 7.5 divided by 2 in the y direction, or 3.75 meters per second squared in the y direction. And that's our acceleration. With that, we've completed the problem. And last but not least, we have Newton's third law. Newton's third law says, let's write down third law. Newton's third law says that whenever an object exerts force on a second object, the second object exerts an oppositely directed force. The second object exerts an oppositely directed force right? So force in the other direction of equal magnitude on the first object. Equal magnitude on the first object. So on the first object. All right, so as a mini example, right, if you get the ground, you get a box, there's you pulling on the box, right? So if you're pulling on the box, right, so you're exerting a force on the box like this. You're pulling on the rope pulls on the box, therefore the box is being pulled like that. Turns out that the rope, as you're pulling on it, exerts an equal and opposite force in the other direction. So this force is caused by, arrow here, pulling from person on the box, pulling from person on the box. And this force is the box pulling back quote unquote on the person. So as another example of the third law, right, we have maybe, let's say, the sun. So this is the sun. Maybe over here we have the earth. Definitely not drawn to scale. But the gravitational force between the sun and the earth, right, they pull towards each other. Right? So the sun pulls on the earth gravitationally just as much as the earth pulls on the sun. All right, so that's pretty much as we're going to get into Newton's third law. So now we're going to talk about types of forces. Types of forces. So as of time of recording, there are only 4 known types of forces in the universe. In order from strongest to weakest, we have the strong force. I know, very cleverly named. Strong force. And it has a range of about 10 to negative 15 meters. So a range of 10 to negative 15 meters. Actually, let me scoot this over like this. So this distance is about the diameter of an atomic nucleus. So roughly the diameter of an atomic nucleus. Right. And then after that, we have the electromagnetic force. Electromagnetic force. Right. It says infinite range. Right. So if you have one electron on one side of the universe and another electron on the other side, given enough time in between, the two will feel each other's presence by this electromagnetic force, right? There's no maximum range for this force. So infinite range, you know, about the size of the universe. So next up we have the weak force. Weak force. That has an effective range of about 10 to negative 18 meters. Range of about 10 to the negative 18 meters, right, which is roughly 0.1% the diameter of a proton. So roughly 0.1% the diameter of a proton. So this is really, really small scale stuff. And last but not least, we have the gravitational force. Gravitational force. So the gravitational force also has infinite range. So the Andromeda Galaxy is very, very far away from our Milky Way galaxy. But we can, like, the gravitational effect of something from the Andromeda Galaxy can still be felt by something in our galaxy. Now that effect might be really, really, really weak because, the two things are very, very far apart, but, the forces can still be somewhat felt. I mean, they're pretty much typically drowned out by other closer objects. So we don't really notice it as much, and we can pretty much leave those very distant massive objects out of our calculations. So out of these forces, which do you think we know the least about? Well, oddly enough, it's actually the gravitational force. So the fact of the matter is that the gravitational force is just so much weaker at laboratory distances that measuring is just really difficult, and it requires a fair bit of ingenuity and cutting edge engineering. So if you guys are curious about more information about that stuff, like how we can accurately measure gravitational waves, for example, look into the LIGO experiment. It's actually really fascinating stuff. And it's the gravitational force that we will be looking at in more detail for the final section of this lecture. Now, for our purposes, the gravitational force is the force between two objects with mass, right? The magnitude of the gravitational force between two objects, right? Literally two objects with mass, is, for the gravitational force, write down the second title, I guess. So we have the gravitational force and we have that the magnitude of the gravitational force between two massive objects, which we denote by F of G for gravity, is equal to G times M1 times M2 divided by R squared. So here, G is the gravitational constant. Gravitational constant, also called Newton's constant, and it has a value of about 6.67 times 10 to the negative 11. 10 to the negative 11 newtons meter squared per kilogram squared. So newtons times meter squared divided by kilograms squared. So here, M1 and M2 are the masses of the two objects. All right, masses of the two objects that we're looking at. And R, little r, is the separation distance. Separation distance between the two objects. So last but not least, the gravitational force is attractive, which means the objects are pulled towards one another with a force of magnitude F sub G. So this here tells us how strong the gravitational force is between two objects. And it's an attractive force, meaning that if we have two massive objects, like we saw in the sun and the earth example. So if we have two objects like this, oh, that is a bad circle. So we've got two objects like this. Let's pretend that these are the center points. Then the distance between them, between their centers, this is our R distance. Let's say that the mass of this first one is M1. The mass of the second one is M2. And so we're going to have some forces that look like this. Or we have one force pulling M1 towards M2. And then another force pulling M2 to M1. So this is F21, right? We can think of this as force, the gravitational force of object 2 acting on object 1. which means that this force over here is object 1 acting on object 2. So that's how we read that. So let's do an example. So this is example, what was the last one we did? Example 3, and this is going to be example 4. Example 4. So the question goes, what is the gravitational force between the Earth and the Sun? What is the gravitational force between the Earth and the Sun? Well, we're going to need some background info. To begin with, we need to know that the mass of the Sun, which I'm going to call m sub s, mass of Sun, it's going to be 2 times 10 to the 30 kilograms. It's quite heavy. The mass of the Earth, let's say m sub e, it's going to be equal to 6 times 10 to the 24 kilograms. Furthermore, we need to know how far apart these things are. So apparently the distance between the Earth and the Sun, or the centers of the Earth and the Sun, it's going to be equal to 150 times 10 to the 9 meters, unit of distance. And then just as a reminder, the Newton's constant G, right, big G, is about 6.7 times 10 to the negative 11, and it has units of newtons, meters squared, divided by kilograms squared. All right, so the magnitude of the force between the Earth and the Sun. All right, so we're looking for F sub G. Right, is equal to G times the mass of the Sun times the mass of the Earth divided by the distance between them squared. So we have G, which is 6.7 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. And you'll notice that G here, the units of G allow us to take this stuff and convert it to a force, right? So if you notice that kilograms squared on the bottom, so that'll convert, or that'll get rid of these two, and that there's a meter squared up top, which will get canceled out by the distance down here. And so this G, when you multiply it by this bit here, will turn all that stuff into a force. So the units just work out. It's not particularly important that I point that out, but it's still nice. So in the numerator, we have 2 times 10 to the 30 kilograms. We have the mass of the Earth, which is 6 times 10 to the 24 kilograms. And then in the denominator, we have 150 times 10 to the 9 meters, and we're going to square it. So if you punch all this in, you get that the magnitude of the force of gravity between the Earth and the Sun is about 3.6 times 10 to the 22 newtons. Right, so that wasn't that bad. Now, last but not least, I'd like to talk about weight. So the weight of an object, right? And please don't get weight and mass confused. They're related, but they're not the same. So the weight of an object, on or above the Earth on or above the Earth is the gravitational force that the Earth exerts on the object. Exerts on the object. Now, this definition is a little Earth-centric, right? Because, you might have heard things like, well, if you go to Jupiter, your weight will be, some number larger than your weight on Earth. The weight can be better described as your mass times the acceleration due to gravity wherever you are, right? So I would like to point out that the weight of an object is a force, right? The weight has both a magnitude, how much you weigh, and a direction. Now, on Earth, that direction is towards the center of the Earth, right? It's going to be pointing downwards because your weight is pulling you down. That makes sense. Now, in equation form, what I've just written down looks like this. The weight of an object, denoted by W, is equal to Newton's constant G times the mass of the Earth times whatever mass we're looking at, divided by R squared. Where R, again, is the distance between the center of the Earth and the object, not the surface of the Earth, the center of the Earth. So in our last example for the day, so this is example 5, I guess. Yeah, 5. So example 5. Example 5 wants us to find the weight of a person. Find the weight of a person with mass of 100 kilograms. So with mass 100 kilograms. A, standing on the surface of the Earth, standing on the surface of the Earth. In part B, 600 kilometers above the surface of the Earth. Not meters, kilometers. Above the surface of the Earth. All right, so let's draw a picture. So if we draw the Earth as a sphere, all right, so we have about the center of the sphere, which looks like this. So the radius of the Earth looks like this. The radius of the Earth, radius of Earth, is about 6 times 10 to the 6 meters. And just as a reminder, the mass of the Earth is equal to 6 times 10 to the 24 meters, or kilograms. 6 times 10 to the 24 kilograms. Right? And from the problem says that the mass of a person, the mass of the person is 100 kilograms. And so what is the person's weight on the surface of the Earth? So initially, for part A, the person's on the surface of the Earth. So they're a distance of radius E away from the center. So the weight is just equal to G times the mass of the Earth times the mass of the person divided by the distance between the center of the Earth and the person standing on the surface. And if we just plug some stuff in, we get G, which is 6.7 times 10 to the negative 11 newtons times meters squared per kilogram squared times the mass of the Earth, which is 6 times 10 to the 24 kilograms, times the mass of the person, which is 100 kilograms, dividing by the distance between them squared. So that's 6 times 10 to the 6 meters squared. And we get a weight of 1,117 newtons. Like that. So just as a side note, if we take just this part here, right, and we leave off this mass, this little m, right, then this part here is actually an acceleration. So we have, so if we just take g times the mass of the Earth divided by the radius of the Earth squared, radius of the Earth squared, it turns out that this is an acceleration, and this acceleration is g, right? This is just 9.8 meters per second squared. So on the surface of the Earth, right, the weight of an object of mass m, if I could draw correctly, this weight is just the mass times g. So I'm actually going to mark that off because that's kind of an important result. It'll be useful for us. Now in part B, it's the same situation, but now we're a little bit further away, right? So here, as an example, is the radius of the Earth. And apparently we're an extra 600 kilometers away. So let's say that we're actually out here. So this extra distance here between the surface of the Earth and where we actually are is 600 kilometers, which I'm going to call h, as the height above the Earth. So we need to convert this 600 kilometers into meters. We know that h, which is 600 kilometers, well, we know that there are 1,000 meters in 1 kilometer. The units of kilometers cancel out, and we get that the height above the Earth is 6 times 10 to the 5 meters. So the total distance we're away from the Earth, the r that we're putting in, is going to be the distance between the center of the Earth and the surface of the Earth, the radius, re, plus the distance we are away from the surface of the Earth, if that makes any sense. So this is going to be 6 times 10 to the 6 meters. Then we have the height above the Earth, which is 6 times 10 to the 5 meters. So this is going to be a radius of 6.6 times 10 to the 6 meters. So that's what we're going to be putting in. So now when we go to calculate the weight, right, that's going to be equal to g, which is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Like that, times the mass of the Earth, which is still 6 times 10 to 24 kilograms, multiplied by the mass of the person, which is 100 kilograms. And we're dividing by the distance away from the center that we just solved for. It's going to be 6.6 times 10 to the 6 meters. And we're going to square that. And we punch all this in, get that the weight of the person, 600 kilometers above the Earth, is 922 newtons. That's the answer for part B. So notice, right, the answer that we got for part A was when we were on the surface of the Earth, which is 1,117. But when you're further away from the Earth, more specifically 600 kilometers away from the surface of the Earth, you only weigh 922 newtons. I don't know if you guys remember back when we were talking about projectile motion stuff or free fall stuff, but the further away you get from Earth, right, the larger this R value becomes, the weaker the force of gravity is on acting on you. So it makes sense that the further away this person is, the weaker the force of gravity pulling on them is. And so with that, we pretty much talked about everything we need to talk about in this lecture. I'm going to save the rest for tomorrow's lecture. So see you guys then.